Hello and welcome to Chapter 8 on momentum. So what momentum is given by the equation P, which is momentum is equal to mass times velocity. So basically what momentum ends up being is how hard it is to stop or to start something. So when we talked about forces and Newton's second law, we said that uh, the force, which is the mass, was defined as how hard it was to move an object to keep it going, and the force could be defined as mass times acceleration. The force can also be defined as the change in momentum over time, where the change in momentum over time is probably a little bit better of a measurement or better of a definition because it allows us to do more things by talking about the change in momentum. So uh, forces can be defined as the change in momentum over time, which is, you'll see if we look at this equation, P equals mv, then the change in momentum over the change in time is just going to be m times the change in velocity over time for something that doesn't change its mass, which is just going to be m times a, which is equal to the force. So like force, like we talked about in force, momentum goes up with mass, and it is also harder to stop something that is moving faster, which has a higher speed, has a higher velocity. So if you stop uh, if you try to stop something going twice as fast, it will be twice as hard to stop. And if you try to stop something going the same speed but with twice as much mass, then again, it will be twice as hard to stop. So uh, because momentum is the change in, or because force is the change in momentum over time, then when you have a constant, or when you're trying to stop something or change its momentum, uh, if you increase the time that it takes to stop something, then that's going to decrease the force that it takes to stop something, because force is equal to the change in momentum over a given time. If you increase the time, then that decreases the average force that's applied when you change the force, or when you change that momentum, when you cause that change in momentum. This is also the first big example that we're going to have of conservation laws. So conserved quantity is something that doesn't change given certain values, certain parameters. A conserved quantity is something that doesn't change. So because of Newton's third law, uh, if there is no outside force applied, so if there's no gravity, if there's no friction, if there's no truck that coming in and plowing through your system that you didn't take into account, then the total momentum is conserved. So the reason that this is a consequence of Newton's third law is that because a change in momentum is equal to a change in force over time, when you apply a force over a given time, that's going to cause a change in momentum in one object. But then by Newton's third law, that object is also causing a force in the opposite direction on the other object, if you remember that. And that change in or that change in momentum is going to be equal to the opposite of the change in momentum caused by the one object. So when two say cars collide, the car if one car is going just a second, let me annotate this. It's not letting me for some reason. There we go. So if you have a truck speeding down the highway and it collides with a small car, then what's going to happen is that the truck is going to be moving less fast than it was earlier, or it could recoil completely, while the car is going to gain momentum. So the truck loses momentum and the car gains the same amount of momentum that the truck lost. So the total momentum of the system, the momentum of the truck plus the momentum of the car is going to be constant, even though there was a change in momentum after the collision when the truck set the car moving, or when the truck set the car moving, it gave it some of its momentum. So because of this, if we want to do the mathematics, we can use this to find the final velocity after collision, or to anticipate which direction and which speed billiard balls or any object are going to go after they're hit by another object. And here are all drawings. The next thing that I want to bring up is angular momentum, which is very similar to linear momentum, except instead of, so it's not really defined particularly in this book, which also goes for a theoretical view of angular momentum mostly. But basically, instead of talking about a the linear quantity, like how much linear speed you have, you talk about how much angular speed you have, and a quantity called the moment of inertia, which is given by the value I. So in this example, in this kind of famous example, or kind of useful example that most textbooks use, you have a figure skater circling around, going around, rotating with a certain angular velocity, angular speed, omega, and I, which is value given that depends on how far out the mass is, how far out the average value of the mass is. So it depends on where you place the mass in addition to just the mass itself. So this figure skater has a constant angular momentum, which is given by L equals I omega. And then once they bring in their arms and make it so that they have a lower moment of inertia, which is what happens when you change the position of the mass of an object, then it's going to conservation of angular momentum, which is the same, which is something that happens as long as you don't have something called a torque, which I think we went over. Conservation of angular momentum uh, states that the the momentum that the skater initially had, the angular momentum the skater initially has is equal to the angular momentum the skater finally has. So as they lower their moment of inertia, their angular speed goes up and they spin faster. So that is the about as far as we're going to get into angular momentum for the moment. But there is also something about elastic and inelastic collisions. So elastic and inelastic collisions occur when two objects bounce off each other and conserve both kinetic energy and momentum. So we're going to get into what kinetic energy is uh, later, but because, or we're going to get into it in the next chapter, but because kinetic energy is also conserved in this case, you can use it to solve for the final velocities in more complex systems. And then a perfectly inelastic collision occurs when two objects stick together after a collision. And this requires kinetic energy to be lost to other forms of energy, such as sound, heat, chemical bonds, and whatnot, while the momentum is still conserved. But most collisions land somewhere in between a perfectly elastic and a perfectly inelastic collision. So that's about all that I have to say about this chapter. Thank you for watching, and I'll see you again soon.